Another new CPL solo paper came across my desk this morning. This one from our Chinese representative. The authors on this paper came from Southeast University in Nanjing, China, as well as East China Normal University. But I see there's also representation from the US from Kent State University, the Materials Science Graduate Program. Just a bit about this paper, again, utilizing CPL. The introduction tells us the ongoing research for highly efficient organic emitters is motivated by their widespread applications in organic light-emitting diodes, OLEDs, photodynamic therapy, data optical transmissions, and information encryption, among others. However, traditional fluorophores often suffer from aggregation-caused quenching in the condensed state, which limits their practical applications in situations where high concentrations or even solid-state materials are required. In recent decades, the concept of aggregation-induced emission has been introduced, which has significantly improved the performance of fluorophores by restricting the non-radiative decay of intramolecular rotations, vibrations upon molecular aggregation. To the best of our knowledge, this is the first time that I'm jumping down a few paragraphs. To the best of our knowledge, this is the first time that non-classical hydrogen bond has been used as the sole key factor in the design of efficient solid-state organic emitters. Furthermore, the system demonstrates remarkable flexibility and potential for diverse applications, e.g. the incorporation of chiral anions enables circularly polarized luminescence, while extending the axle of the Rotaxane structure allows for the development of stimuli-responsive fluorescent materials. More importantly, the system provides a platform to study non-classical hydrogen bonds, not only for organic luminescent materials, but also for a wider range of fields. And then I want to jump down to applications in circular dichroism, circularly polarized luminescence, and simply state that the utilization of chirality transfer from chiral anions to fluorophores to achieve CPL is challenging, since it is difficult to obtain a relatively close spatial distance between anion and cation using electrostatic forces alone. In the solid-state system described above, the strong binding driven by non-classical hydrogen bonds provides a potential pathway for chiral transfer. The circular dichroism spectra of the two fractions of each Rotaxane, 10 or 11, had the identical intensity and mirror image peaks, which was consistent with the relationship between corresponding enantiomers, figure 6. Despite the absence of CPL signal in solution for Rotaxanes 10 and 11, the CPL test conducted in the solid state revealed the presence of robust CPL emissions for both Rotaxanes 10 and 11, suggesting an effective chirality transfer in the solid state. The corresponding enantiomers revealed almost mirror image CPL peaks with opposite G-looms, i.e. a positive CPL signal for Rotaxane 10R and a negative CPL signal for Rotaxane 10S, with the G-loom value of 2 times 10 to the minus 3. So again, another application or types of applications for circularly polarized luminescence. This particular paper just came out, I believe it must have been in May of 2025. So if you're interested in learning more about this or about the CPL solo that was used for this research, please be in touch. Thank you.